Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question raw and the cuts. So we have a hard today. It's called largest color value in a directed graph. So let's see what it wants. So there's a directed graph of n color nodes and m edges, and the nodes are numbered from 0 to n minus 1. You're also given the string colors. So yeah, string colors, where colors I is a lowercase English letter representing the color of the ith node. So you're also given a 2D array edges where so those are just the edges, and they're actually direct edge. So it's not like it doesn't go both ways, it only goes one way. So what is m and n? Right, so they're both 100,000. And colors only consists of lowercase English characters. So there will only be 26 colors in this case. And obviously for the edges, like the nodes has to be like between 0 and n because of how the nodes are numbered. So a valid path in the graph is a sequence of nodes such that there is a directed edge from xi to xi plus 1 for every there is a directed edge from xi to xi plus 1. So I'm thinking like these x1 x2 are just like the number of the nodes. So the color value of the path is the number of nodes that are colored the most frequently occurring color along that path. So we want to return the largest color value of any valid path in the given graph, or -1 if the graph contains a cycle. Right. Yeah, maybe we have to look at some example first. So for the first example, we have this graph here. So AB, ACA, so like 0 would be A, 1 would be B, and then like you have ACA. So yeah, I'm guessing like this path is the path with the most color, I think. Okay. So yeah, okay, so we return 3 here because like for the longest path, well, we have 3 reds in there. Well, 3 A's in this case. So the path contains 3 nodes that are colored A. And then example 2 is just 0 that points at itself. And we will return -1 because there's a cycle. We actually... Is it that if it contains any cycle, we want to return -1? Yeah, actually that makes sense. So if you imagine like even if you have some bigger cycles, right? So let's say something like this. If there's a cycle, you can just keep taking this cycle to get like infinite amount of color, right? So yeah, so that's why like when we're actually dealing with the path with the most with the most color, like frequency, we actually don't have to deal with any cycles. So yeah, I don't see an immediate solution, but if we have a cyclic directed graph, I think like usually that makes things a bit easier. So what I'm thinking is so for a cyclic directed graph, you have some sort of order. So like for example, for the first case, you have like 0, 1, 2, 3, 4, right? So you have something like this. Yeah, also before that, another observation is well, technically, because we only have 26 colors, and if we run I don't know, like any n or n log n algorithm on the graph, we can technically deal with each color separately. So like for example, we only add one when we see a color A when we are like dealing with color A. We only add like one like when we see a B, like when we're dealing with color B and so on. So that's like another way to that's like another way to turn our problem into like an even smaller subproblem. So hopefully that makes things like even easier to deal with. So yeah, in this case, so let's only like circle the ones with our desired color. And I think like so actually these graphs are directed, right? So actually we want to go from the roots. So basically in the topological sort in the topological kind of kind of thing, a root is defined by any nodes that don't point into any other any nodes that doesn't have an edge pointing towards it. So for example, like right now 5 and 6 are both roots because nothing is pointing towards it. 5 is still a root because you can point out, but you just can't get pointed inwards. But so for example, like right now 6 is no longer a root. So we want to start at the root. So it would be like 0 and 5 here. I don't know, let's say 6 is like 6 has our desired color, let's say. Right. So we start at the top. And then I think like we can kind of use a DP kind of technique. So it's technically like not really DP, but it uses like kind of a DP idea. So like if we do see a blue color on 0, and when we move to its children, we just want to get the maximum. We just want to get the maximum of that color. So yeah, actually it is just DP. So like for example, we want to find from 0. Yeah, okay, so this is my idea, right? You want to find from 0 what is the longest path from 0? So like 0 has to be the starting point, right? What is the longest what is the largest frequency we can achieve? Like if we start at 0. Well, 0 will have like a few out paths that goes out, right? So when we get to 2, we want to know the maximum know the maximum frequency for 2, and then 2 would just like go to each of his like children to like try to find out the answer. Yeah, and then like for 3, and then like it will go to 3, and then it will go to 4. Well, it will also go to 6. Yeah, so we can kind of like use DP for this actually. But like of course we have to find all the roots first at the beginning, and we also have to like check whether there are cycles, and like if there are cycles, like we'll just return -1 early on. So yeah, but when we reach a leaf node, well, all we have to return is whether that leaf node has our color or not, right? So if it has our color, which in this case, yes, like it will return 1 here. And what will 3 return? It will return 1 plus whether it has the desired color, right? So in this case, it will just be 0. And then when we get back to 2, well, actually 2 has like two different ways, right? So like you have 1 here as well. So both of his children returned 1. So we want to get the maximum of that, which is just 1, and then we add whether 2 has that color. So it will be 2. and well, it would be like 2 plus 1 is equal to 3 here. Sorry. Yeah, unless well, unless like let's say this path is like 4, then like we'll take the maximum of like that, and then we'll return 5 here. Uh, so yeah, I think that should work. Um, yeah, so I think like other than that, we just have to check for like we just have to like do the very standard way of like checking for cycle and also like finding roots and stuff. Yeah, I'm a tiny bit sick because of the seasonal change. So yeah, but I think we can start coding. I'm slightly worried about the recursion here. Like again, I'm scared of like the stack being like too large or something. Um, if it is too large, we might have to like whip backwards or something. Yeah, actually, would that be a safer way of doing this? So um, instead of like going down, because like we can have 100,000 nodes, right? So that means like you can go from like 0, 1, 2 all the way to like 100,000 here. So that means like because we are recursively calling for the DP state, we'll have to call like 100,000 times here, which might like which might make the recursion depth like exceed or something. Um, well, I guess, but that's like the nicer way of doing this. So, honestly, let's just try to do this first, and if it doesn't work, we'll try to do the other way, which is like go from like bottom to top. Yeah. So let's just code it up now. So the first thing we have to do is we have to try to find cycle, and then we have to find. I guess like the first thing we can do is so create adjacent list and find roots. So we have roots, and now for AB and edges. Yeah, I guess like what we can do is we can do like children's. So we can do children's here, and basically we can use a set maybe. Oh, I got an even better idea. Like we just use a set here. So this would be like 0. Wait, I for I in range. How do we know what n is actually? It doesn't provide you with what n is. Well, that's quite annoying. So that means like we actually have to find number of nodes in our graph first. So I guess what we can do is we just do like n is equal to the max of max e for e in edges. So that'll get the max between the two edges, and then like we'll get the max there as well. So I guess we can also check like if A is equal to B, like we don't have to deal with any of the self cycles, because I'm not sure whether my find cycle algorithm actually deals with self loops. So might as well just deal with it here. So if it points at itself, then obviously there's a loop. We also need adjacent list up here. So for so we can use n right now. Oh, actually, it should be n plus 1. Yeah, because like for example, if the largest is 4 here, we would have we will actually have 5 nodes because it is zero indexed. Yeah. So you need to create an list in our JSON list. So otherwise we'll just do that and then append B, and then we'll do that, append A. Yes, and also if a node is at B, that means that means we don't that means like the B node can't be a root because A is pointing at it. So we just do roots remove B. Yeah, and when we get to here, also one thing is if there are no roots, that means every node is being pointed at, and that means there is a loop somewhere. Because like any node you start at, actually is that even true? So if we have a graph where like could it be that like I couldn't think of like a straight proof for this, but I think if there are no roots, that means you can always form a cycle, which kind of makes sense. So yeah, I think I'll go with that. Yeah, I think I'll go with that. Yes. Yes, so that there's something called like there's something called back edges, which basically means like for any graph you can form a tree for any graph. So like for example, by doing DFS or something, right? If there's a cycle, that means there will be a back edge. So a back edge is basically an edge that goes from a lower layer to a higher layer. So maybe something like this, right? Yeah. Oh, actually, yeah, I think like with this in mind, if we don't have a root and we have a DFS tree, so something like this. So we can pick any node as like our root of the DFS tree, right? But we know that this node cannot be a root. So basically what that means. Oh wait, that node can like that node. Yeah, that node is not a root. So that means like somewhere we have a node that points back to it. So so that means there will be a loop. Yeah. So yeah, I'm right on the like if there are no roots, there is a cycle. Yeah. Also, could it be a like could it be a graph with multiple components? That's another question we have to think of, I think. Which does make the question quite annoying to deal with, because now I think we have to go to each. Yeah, I think like what we have to do is we have to look at each root, and like when we're doing the cycle thing. So like for example, you can have like 0, 1, 2, 3, then you have like 4, 5, 3, something like this, right? But it just means like we have to keep track of what we have seen so far. So like for example, we have seen 2 here. So when 4 goes into 2, because we have checked like all the children of 2, right? And we know that there are no cycle there. So like let's say when we're dealing with this tree here, so after like because we have checked that, and like if 2 goes to like 5 or something, right? We will have checked that already. So we don't actually have to like deal with that again. So yeah, I think like we just need a scene array for this actually. So we have scene set. So now if length roots is 0, again like we talked about it, it'll just be nothing there. Yeah, so yeah, also we need an isActive set. Yeah, actually a set will be quite slow, but whatever. So now for root in roots, so we want to DFS into all of his children, right? We can call it like find cycle. So find cycle, we have like I, which is an int. So what we can do is we can go into all of its children. So for child in I, we call it node. It's a better name. Yeah, so we want to like find cycle for the root. So we start at the root. We go to each of we go to each of the children. So if the child is active, well, that means. So if a child is active, what does that mean? So let me draw up. Yeah, let's look at like this graph here, right? So let's say we start at 1. Well, even though it wouldn't really be a case because 1 is not a root, but like when we go to 2 and then like we go to 4, so 4 will go back to 1, but because 1 hasn't checked or is like it hasn't finished with all its children yet, it is still an active node. So like by keeping an active array, we can like find loops basically. So if it is active, I guess we can just return true. Yeah, we can just return true in that case. So if find cycle, again we want to return -1 here. So otherwise, yeah, actually we need to set our node to be active before that, and then after we are done with everything, we just remove the node like from the isActive thing, and then like we can return false here. Yeah, so what we can do here is if find cycle child, so if it does return true, we want to return true. If it returns false, we just go to the next child. But what that means is we also have to check whether we have seen a node yet. So I think like we only want to set the scene thing. So scene.add node. We only want to set it once we are done with all of them. So like we have made sure that that node doesn't actually form a cycle anymore, and we can remove that. So I think that should work. So find cycle, return -1, and then of course the last thing we have to do is we have to do a DP. So do DP on all roots, something like this. So for root in roots, I guess like we need a function called like def max frequency, let's just call it that. And then again, we have a node as well. And actually, I think we can. So remember, like the A to Z thing that I talked about. I think what we can do is we can just create a length 26 array to store like all the colors at the same time. Okay, so of course we have the base case first. So if adjacent list node is empty, so we just do not. So if it is empty, that means it is a leaf node, right? So if it is a leaf node, we just want to return I think like 0 for I in range 26. If it is not the correct color, we'll just return that, right? So we just do. So how do we get the color of node? Well, we just do colors node. So that gives us a color, right? I think it's like minus ordinal. Yeah, we can just do ordinal and then ordinal of A. So that will give us the. Wait, actually, yeah, that will give us the correct color. So if I is equal to that, else, like for all the other ones, we just return 0. So that's the base case. Otherwise, actually, I think we can just do this, right? So, yeah, we can just have the result, and then, so we can initialize with this. We can just return res here. So otherwise, we do have to go into each of the children. So for child in JSON list node, I guess like we want to store the result outside already. So let's call this like frequency. And then, so we should have the result for for each of the node, but initially it would just be none. So like when we check there, if it is none, then we know that we haven't looked into that node yet. So for range n, so that's all the nodes. Return res for child. Yeah, actually, maybe we don't want to return this. Like we don't want to return anything. We just want to store it in res. So res node is equal to frequency and then return. Yeah, that seems better. So if child, so if we haven't seen, like if we haven't evaluated the child yet, it's none. We want to evaluate it, right? So we want to run max frequency for child. And after we have done that, we just want to check for like each of the frequency. So we can call it like child frequency would be equal to res child now. And then so frequency would be equal to I guess we need to like get the max. I think there's a zip function. I'm not sure if I remember how to use it though. I think it's something like for AB in zip. So zip, like think about it as like a zip lock, right? So you have like I don't know, like 0, 1, 2, and then you have like another array 3, 4, 5. So zip basically creates like tuples like that. I think that's what it does. But I could be very wrong. Let's just go with this for now though. So child child frequency. So we want to get the max. So like basically we want to get the running max for this. So we get it for every children. Um, okay, maybe we do this outside. So what we can do is we can just do, so for here, we can do frequency of colors node ordinal minus ordinal A. So that will give us the correct index, right? Like we'll just add 1 to that. And at the end we have to add 1 to that as well before we return. So because like right now frequency would only like have the maximum for each color from its children. Oh, it's actually rest node. That means there's something wrong here, right? Oh no, it's because it's frequency. Is that correct? That looks right. Yeah, okay, and then of course now we put the frequency out there. Yeah, and then what do we do now actually? So I think we just run max frequency for each of the root. So max frequency from roots. So that will allow us to get to dynamically get the maximum frequencies for each of the roots. And then I think for outside we should have a we should have a rest frequency. So this should just store so this should just store the maximum, the current running maximum, because the answers from the roots are definitely optimal, because for example, for 0, if we don't use the color 0 here and we only look at 2, 3, 4, yeah, it will give you 2. Even if 0 is yellow or something, it will still give you 2 for red. So that means we can just check the best answers from the roots. So again, for rest frequency, we'll do something similar up here. So so if the zip thing works, it should just be rest frequency and rest of roots. So yeah, and then we just return the max of rest frequencies. So that will be the best color. Let's fix all the bugs now. Int is not iterable for child in adjacent list node. So you return a -1. Yeah, okay. Of course that returns -1. We actually want a 3 here. So what went wrong? So I think it's my find cycle thing, which honestly I'm not confident at all on finding cycles. If find cycle child so the only root should be 0. Actually, yeah, let's print out our roots. So print what we can do is we can just print root here. So root just do that. So that's how we know what roots. So yeah, we have only looked at 0. So that means 0 goes into these things. I guess what we can do is we can print out which node we are going through as well to try to find out what the issue is. So it goes to 1. I did a stupid thing here. It is a directed graph. But I did both ways. Okay, looks promising. I'm not sure how correct this would be though. Like especially with the zip stuff. Oh no, we have a key error. That's not good. Yeah, let's get this test case, which is kind of it's a pretty big test case. So what is the expected actually? Yeah, let's just run this first to like try to debug it. So roots remove. So when we are removing, where is it? Oh, here. We should use this card. Yeah, okay, I see the problem here. So, like, let's say we have like both, maybe I should stop using red. Let's say we have like 1 and 2 pointing towards 3 at the same time. The first time we will, sorry for the voice crack. The first time, when we look at one, like the edge 1, 3, it will remove 3 from the roots, right? But for the remove method, if we try to remove a non-existent key, it will just return an error. So, but if we use this card, like if B is like no longer in roots, it will just do nothing. Okay. So let's see if we have any more bugs to fix. We do. It's an empty sequence. Oh. Right. Oh, wait. Actually, I just realized you can just use linked colors for you can just use linked colors to get the the number of nodes. How did I not see that at the beginning? Okay, right now I'm like 80% confident it works. Oh, unless it times out, then like we could have reached like max recursion depth or something. Oh yeah, we time limit exceeded, which is kind of annoying. Well, actually, this case is not even that big. So, my hypothesis is that something is wrong for my find cycle thing here. So I guess like one very easy way to like try to find out what's wrong is just print all the nodes, and hopefully it actually does print the stuff here and not just say like time limit exceeded. Yeah, pretty sure it is the cycle that's wrong here. Output limit exceeded. Okay, so let's see where the cycle is. Like we should see the. Okay, so yeah, we have a cycle here. So that means we are not actually dealing with the cycle correctly. Yeah, I'm not that good at finding cycles. I need to get better at it. But let's try to find out the problem. So when we get to 94, it goes to 95. So it's going to turn that into its active. And 95 goes to 83. Well, remember this is a DFS because we always check first. Yeah, so find cycle, and then 95 goes to 83. So now we will have is active dot add in there. But yeah, it should still be in this loop. So like for example like 94 should still be in is active. So for child in like the adjacent list, so obviously it is inside there. That's why it is in there. So 94, 95, 83. Hmm. So child in is active. Yeah, we just want to return in this case. And when we find cycle, like if we do actually find the cycle, it should just return true for all of these. And then I guess like after we set return true, we want to so after like if we have found the cycle already, we should just like set like basically like when we reach this stage, it should just return like true all the way back like to the first thing. So yeah, we can just do remove node, and then so we can like basically stop any more loops by just like by just forcing like all the nukes to be like is active or seen. This thing doesn't think so. It thinks that it is still wrong. Yeah, I'm not too sure what the issue is here then. Is active find cycle. Is it not returning? Maybe it's because I forgot to do if node in scene, we just want to return false. I think it might be that. Is it that? Okay, yeah, so that was the issue. And now we only have the recursion maximum depth thing to worry about now. Oh, well, actually, we don't have that issue. We only have like one more problem. So let's try to find out what the problem is. So it's AAA. The output is 1, expected is -1 because we do have a loop there, but somehow it didn't find the so we actually don't want to just look at the roots, I think. So for this case, what's actually happening is that you have a 0 and then you have like a 1 and 2. So because like we only start at the roots, we actually couldn't like. So yeah, instead of using roots, here, we should just do for I in range n, and so if we haven't seen I yet, and find cycle I does find you a cycle, we return -1. So I think doing that should work now. Okay. Nice. It worked. Yeah. I think like if I'm better at finding cycles and not forget these little things, it should be a way quicker solve. But yeah, whatever. We got this in like 40 minutes, which is not too bad for a hard question. Yeah, so let me explain like my intuition a bit, I guess. Well, so the first thing is, because if there's a cycle, if there's a cycle, you can just keep like going through that cycle to get infinite amount of frequency, right? So like let's say you have like let's say for this case, you just keep going through like 0, 0, 0, 0 to get like infinite amount of reds. So that's why like you have to return -1 for cycles. And yeah, so I probably won't go through the find cycle thing. I think this is like a pretty standard algorithm that there are like just like way better explanations out there than what I would have done. So I'm just gonna explain like what happens after you found out the graph is acyclic. Well, because it is directed acyclic graph, well, like as I've said before, you're going to have some roots. So there's a thing called topological sort, which is basically if you have an edge A to B in the sorted, like in the topological sort array, A would always come before B. So, like for example, if we have like A and C as well, well actually C could be here or it could be there, but it doesn't matter because A is before both B and C. So that's what topological sort is. The reason we did that is because so for a cyclic graph, we always have a topological sort, and when we always have a topological sort, we actually we can actually like form an order on our graph. So like that's why I've been drawing my graphs like in the top down sense, and so and like basically we're like going from the top layer like all the way to the end. And so now if you think about like the different coloring, so let's say this is like red, this is like maybe let's just look at one color for now, because like for the like if you have more colors, it's like basically the same thing as well. So let's say we have something like this, right? So why wouldn't the answers that are not roots not optimal? Well, um, if you think about it, for so let's say like for one and like I don't know compared to like three or something, right? If the maximum for three, well, in this case it'll be one. Like if we are dealing with red colors, well, that means for one's answer, it will be one or more because three is one of one's, so three is one's child, right? So one have access to like its maximum values. So it has like three's maximum values, right? So that means it will have one, like at least one already. And of course, if one is color red as well, it will obviously be even more optimal. But like basically what that means is like because the parent always gets the children's like maximum frequencies. If we just look at if we look at a parent instead of a child, the parent will always have the better answer. Well, and what are the like the ultimate parents in our graph? Well, it would be the roots. So this is why like if you look here, like I'm only storing the running maximum like from the roots. So that's the first thing. The other thing is, well, if you think about it as like a tree, well, actually, like because it is acyclic, like again, we have some sort of layers, right? So like, for some other DP questions, like I don't know, like if you have like DP and then like you go like this. So if you have to like go from the end like to that way, there's also some sort of like layers, right? Like if you can solve this, like you can use this value to solve the next one, and then you can use it to solve the next one and so on. So this is like similar here, right? If we can know the maximum frequency of red on 5, we can use that to solve for the upper layers. So actually like this is not that good of an example, but let's just draw like another like easier example. So let's say like these kinds of like it's trees as well. So for node 1, we don't actually need to know what's happening below. We just want to know the maximum frequency we can form by, well, like the maximum frequency of, let's say like red colors we can form like with a path like from 2 all the way like to the end, or well like basically just any path in here, it doesn't really matter. So if we have like 3, 5, 4, well, for 1, it doesn't really care what's happening like inside the subtree. You just want to know what the maximum frequency for red color is, right? So in this case, it will just pick 5. And when you have 26 colors, well, like for the array here, where is it? Yeah, for the array here, like even when you're like updating it here, well, it's just doing like for all the colors, but you can think about it as like doing one color like like gradually or something. But like it's the same idea, even with like more colors. And like of course at the end you want to get the best, like the color with the highest frequency, right? So like just return the max here. So that's kind of like the intuition on like how I solve this problem. And like yeah, also like the reason I use DP here is because well, if you don't use DP, that means like you have to like keep going back down. Like so if you have like 1, 2, 3, 4, that means like if you want to evaluate for 4, well, it would just be itself. You want to evaluate for 2, you have to like look at all of his like children and stuff, right? And then for 1, like you have to go down as well. But because we know that like the parent is always better than the child, and like we have this like longest path kind of thing. We know that like we can use DP to like act as a cache to shorten our process basically. So yeah, I think this question is quite interesting. It's also, I would say it's like, it's not too hard. Well, except the whole fighting cycle thing, which I do have to get better at. But like otherwise, like the DP makes a lot of sense. Yeah, I know it is 3DP, which is like not too like, is it even rare? I'm not sure how rare it is. But like 3DP, well, it's like slightly harder than like normal DP. But yeah, I think this is a pretty good problem. And I'll see you tomorrow. Bye.